In this video, we're going to be talking about bivariate distributions, and this is as opposed to what we've previously been talking about, which is single variate or single variable distributions. And those are kind of like this. We've got maybe the width of an object. It's got a mean. Okay, well, yeah, width. We're kind of used to width. But what if we want to see the distribution in one part of not only the width, but something else, like maybe the length? Well, the way to do that, of course, is to, well, if you can get it to work, there is to create sort of another dimension on your plot. So if you've got x, you have a y dimension, and that might have something like length on it. And in that length, you're going to also have sort of a mean. And what's really going on here is you're indicating the second distribution that you're interested in using a new dimension, but you're also using a third dimension, the z-axis, in order to indicate what the actual probability variation of probability is. And here's a sort of a neater look at this whole idea. So you've got two dimensions, x and y, for example, and then a third, the z, indicates the way that that probability is varying along those two different dimensions. So what's this video all about? Well, it's about the fact that many random processes produce two or even more outcomes. So we can have sort of length and diameter of a part that's made by a CNC lathe, or you may have final exam score, right? Your final exam score and the amount of time you spend studying. Note that the two outcomes may or may not be related to one another. So in this presentation, what we're going to do is extend our probability results to random processes with two variables. And we're going to include probability functions, probability density functions, expected value formulas, and so forth. And we'll kind of extend what we've done already on one axis, one dimension, and we're going to extend that so we can talk about two different variables at once. Most of this is going to be along the lines of information we've already covered, but there will also be some new concepts. And whatever we present here, we're extending it from 1 to 2 dimensions. We can easily have 3 or more outcomes. So this is just a sort of a basic extension that can be extended even further if we so desire. So let's start with a good problem. And the best problem to present is that with a bin that's got 56 parts, and 7 of them are defective, which means that we've got 49 are good. And what we're going to do is we're going to select 2 parts at random without replacement, and we're going to let those discrete random variables be x, and x is the first part, right? And y will represent the second part. So we can have a good first part. We're going to represent that good first part with a 0, or we can have a bad first part, and we're going to represent that bad first part with a 1. And we'll use the same nomenclature for the y, for the second part. So good is 0, bad is 1. Now, we can represent all the sort of permutations that can arise, or all the different kinds of flavors of parts, using this table right here. So we can say, well, let's see, this is y is, which is the second part. Y is a good one, so it's a good second part, or y is a bad second part. Or we can have x is a good part, or x is a bad part. So x is good, x is bad. So one way that we can select parts is we can say, well, the first part is a good part, 0, and the second part is a good part, that's a 0. So the probability of that happening is 0.764. Where'd we get that from? Well, let's see. The probability of a good first part is, let's see, we've got 56 parts altogether the first time we pick, and we've got 49 of them are very good parts, right? So that's 49 over 56. And then, but we're picking more than just that first good part. We're also picking a good second part. So what's the probability that the second part would be good? Well, we only have 55 parts when we're picking the second time, and we have, 48 good parts. So this is the probability that the first part was good. This is the probability that the second part was good, which is all shown, right? First part good, second part good, and when you calculate things out, that's the number you get. What about this second one right here? That means we've got, a good first part and a bad second part. So let's multiply that out. We've got good first part is 49 over 56. We already calculated that. A bad second part, that's not this number. It's instead we've got to take, well, we only have 55 parts left. And how many are bad? 7. So if we take 49 over 56 times 7 over 55, that will give us this number right here. So notice what this means. We can have a good first part and a good second part, or we could have a good first part and a bad second part. Either one gives us the probability of having one good first part is these two added together, right? And so that's what we see right here is add 0.764 to 0.111 and we get 0.875. This is the marginal probability that x is equal to 1. Why is it called marginal probability? Because it's at the margin. Now, likewise, we can do the same sort of thing. Look, the probability of y being a good second part, but we've got a bad first part is this 0.11, and then likewise we've got a bad second part, but we've got also a bad first part. That's the probability is 0.014. And if we want to, we can calculate the marginal probability of having a bad first part as being the addition of these two quantities, right? So there we go. That's the marginal distribution. What if we wanted to know what's the probability of having a bad second part? Well, let's see. We can get it two ways. We can have sort of a good or a bad first part. As long as the second part's bad, we can add them together, and that's the probability, the marginal probability of having a bad second part. And here's the marginal probability of having a good second part is just add these numbers right here. So everything kind of all sums up on the margin, so to speak, and even it's as we expect. So look, if we add these two numbers together, they should equal 1. These two numbers together should equal 1. And why? Because the total probability of the x distribution or the y distribution has got to sum to 1. And in fact, this whole thing right here, it's all got to sum to 1. And that's what we expect because it's a probability distribution function. So there we go. The joint probability function of x and y is given by this conditional probability right here. So let's specify exactly what that means. Probability of x is equal to, let's say, 0, right? So we got 0. I should point out that this is, look right here, see how it says probability of x, and so your thinking is kind of along the lines of, well, isn't that, aren't these zeros and ones, don't they relate to x? No, actually, whatever this is actually kind of the other variable. And likewise, this is the probability that, I should say, x is equal to 0. X is equal to 1, right? And so what's happening is the probability of x is equal to 0 intersecting with y is equal to 0 is just this right here, right? And so this is a way of the notation of writing this probability distribution function that we are actually seeing within the table. What we had already mentioned before was that probability of x is basically a summation across all the y variables. See, that's y. So sum up all the y's, and that's what we're doing. We're summing across all the y's, and we're getting x. And likewise, so these become x, these become x, and likewise for y, we sum across the x's. And that's what this is doing, summing across the x's in order to get the marginal probability density or distribution. So notice here that if we're kind of looking the properties of the probability function are all satisfied. In other words, the probability is ranging between 0 and 1, and the summation of everything in between all of these boundaries, right? So summing up over all the y's, summing up over all the x's is going to give us 1. And just kind of taking a little bit of a look at this thing, this is intersection of x intersecting with y, so any particular one, which is the intersection of that x is equal to, 1, say, or 0, and y is equal to 0, is equal to, and we think of it like this, the probability that x is 0, which is the first that we picked is 0, and then times the probability that given that the first one was 0, that the second one is, let's say, 0 as well. So that's what we see right here. And this is just, all of this is the conditional probability theorem. It just says given a certain value, x is a certain value. This is saying given that the probability that x is, say, 0, right? So probability of x is 0, and then given that the probability of x is 0, y is whatever we choose. These two probabilities multiplied together are just this number right here. Now, probability of, given that x is some value, we've got y, that's called the conditional probability function, and these ones on the edge are the marginal probability distributions here. So this is probability of x, that's the marginal probability. These ones right here are probability of y. And note that we can swap around x and y in these functions up here, and everything still works just dandy. For many discrete bivariate distributions, a closed form does not exist. So that means we just put things in a table, kind of the way we already did. And the table usually also has marginal probability functions. So for this example, we can say something like this. If we've got a random variable y, and it's got its numerical values 0 and 1. Remember, this is y, this is y, this is x, this is x. So we've got x is equal to 0 or 1, and then we've got the values for the actual joint probability function within the table. Here we've got the values for the marginal probability function, right? So marginal probability function of y. And that's just the summation. Notice there's the summation as it's coming on down of all the x's. And in a similar way, the marginal probability function of x is shown here. And that's just taken by adding up over all of the y's. So everything has to sum to 1. That's the deal. So either add up here, sums to 1, add up here, sums to 1, or add everything up in the middle and it sums to 1. And this is a very good check to use in examinations. So let's take a look at a typical example. This one involves an engineering statistics class, much like our own, that has 40 students in it. 60% are electrical engineering majors. So that means what? 24 actual students. 10% of them are industrial engineering majors, so that means 4 actual students, right? And 30% are mechanical engineering, so that would mean 12 actual students. So we're going to sample 4 students that we select randomly without replacement. Aha! Without replacement. So that means that we are going to have the general hypergeometric. So we're going to let x and y denote the number of industrial. So x is industrial engineering students. And y is going to be the number of mechanical. So since it's general hypergeometric, we can already kind of get a sense that what we're going to need is an equation that will calculate the probabilities of selecting each of these kinds of students that looks something like this. That for any given x and y, and we don't need to calculate what the electrical engineering majors are, because once we know industrial and mechanical, well, that automatically sets the number of electrical that we have. So anyway, so if it's general hypergeometric, the probability of choosing any industrial and mechanical students, which automatically sets the electrical, is going to be, let's see, well, we've got 4, right? That's 4 industrial engineering majors, so however many of those that we choose. And then we've got 12 mechanical engineering students, so however many of those that we choose. And then 24 choose, well, whatever's left over. So we can only choose 4 maximum. So 4 minus the number of industrial and mechanical students is sort of how many different kinds of combinations that we can choose of each one of those. Divide it by the total number of combinations that we can choose. So we've got 40 altogether that we can choose, and the total number of combinations is going to be 40 choose 4. So if we take that, and we remember that this is for x plus y is less than or equal to 4. And we kind of have to figure out what the probability is for every single one of these possibilities. So let's do this for the first one. We're going to say if x, well, let's do this over here. X is 0 and y is 0, then what are we going to get for our probability fxy? Right? So what does this number turn out to be if we plug in x is 0? In other words, 0 industrial engineering students, 0 mechanical engineering students, and everything is electrical. Well, we start plugging. So I'm going to just plug into that equation up there. It's going to be 4 choose 0 and 12 choose 0. And then it's 24 over 4, or choose 4 minus 0. All of that over 40 choose 4. And if we work it all out, let's see, that turns out to be 1, right? 4 choose 0, well, there's only one way I can do that. 12 choose 0, there's only one way I can do that. And then 24 choose 4, well, that turns out to be, let's see, 1,600, or 10,626, all divided by 91,390, which all turns out to be 0.16271. So we've got that number, and basically what we've got to do is we've got to calculate this for every single possibility. Magically, I have done this for you, so you can see right here that the first calculation of this probability is right here. That's what we just calculated. And that is for x is equal to 0 and y is equal to 0. And if we go through and we continue to calculate for each possibility, we're just plugging in x is 0, y is 1, x is 0, y is 2, and so forth. All through this, we'll come up with this nice nifty table. Now, so this is the first thing they've asked for, basically, which is this probability, set of probability distributions. So we've got it worked out. Now the next thing we need to do is we need to work out this one right here, which is the probability distribution function of f of x. So this is actually pretty easy. All we need to do for this function is, let's see, well, basically we're going to draw up a table, and we want to know the distribution of x and given any particular value of x. Whoops. So we just make up a little table. And then all we have to do is, let's see, so when x is 0, well, that's all of these things right here, right? So all we have to do is just add up all the x's equal to 0. So if we do that, we will get, so I'm just basically adding all these probabilities, we will get 0.64445. And for 1, we're going to get 0.312507, right? So what is that? We're taking this right here. We're adding, those are all the probabilities of x is 1. So we're adding those all together, and that's what we're getting here. And let's make something that looks a little bit neater. And voila, we've got everything all worked out here, and it looks kind of nice and neat. And you can see for x is equal to 3, all we've done is taken all these x's of x that are equal to 3, added them together, and likewise for x is equal to 4, it just turns out to be the same thing because there's only one way to do it. So now we've just figured b out. That's this table right here. Now we want to find what the expected value of x is. Well, gee, that's really actually pretty easy. We can just use our handy dandy old formula. So we sum up x, f of x, and that is simply going to be, well, let's see, take this 0 right here and times the probability of that particular function, which is going to be 0.6445. So that's 0 right there. So now we're going to add it to what? Well, obviously we go to the next one, which is 1, and the probability of 1 is going to be 0.312507. And then we're going to kind of keep going through here. And it all magically adds up to 0.4. So that's our expected value of x. Now for part D, we are asked what is the, maybe a better way to write this is the distribution of y given that x is equal to 3. So to calculate this, basically what we want to do is we want to live only in the world where x is equal to 3. So we already know what the probability of that is. It's right here. That's x is equal to 3. And so that means that given a base where x is equal to 3, right? Let's see. Well, there's two ways we can calculate this number. We can either grab it off of this table, or we can look over here and say, there's two ways that x, can equal 3, and that is 0.0105. There's that probability, and there's 0.00525, right? That's the whole world of probabilities that we can get x is equal to 3. And coincidentally, those two numbers equate to this number right here. So then all we have to do is, there's only two ways you can get y in that world, right? Y can be 0 and y can be 1. So what is the probability that, let's see, that y is equal to 0? Let's see, that's this probability right here. So within that whole world of x is equal to 3, the probability that y is equal to 0 is going to be 0.00105, same number as we've got down here, no surprise. And if you figure that number out, that ends up being 2/3. So within this whole world of x is equal to 3, we've got a 2/3 chance of y being equal to 0, and obviously we're going to have, let's see, 0.00. We're going to have 0.00525, right? So that's a smaller chance. And this is the chance of y is equal to 1 within only that world, and that is 1/3. So basically we can write that the probability that y is 0, given that y is 0, given that x is equal to 3, is just going to be 2/3, and the probability of y is equal to 1, given that x is equal to 3, is just 1/3. Now if we wanted, we could make a nice little table that's that shows exactly these results. And there you go, there's our nice, neat little table that sums up exactly these results for the values, for the probability of y given that x is equal to 0. So now let's work out what's the expected value of y given that x is equal to 3. Since we've devised a nice, neat little table, that makes it easy for us. All we have to do is calculate, right? Expected value of y given that x is equal to 3 is just use the same old formula. We're going to take 0, right, times 0.6667, right, 2/3. And let's see, it's going to be the value of y is 1 times that probability of it occurring is going to be 0.333, and all of that ends up being 0.3333, and you can keep going if you want to, but okay, so that was pretty easy to calculate, and actually the variance is also easy to calculate. We just go back to our old formula for variance, which is simply that if we've got the variance is just the expected value of x minus mu, minus mu squared, and that is just summation over x. And I'm just giving the general formula here, so that's why I'm using x, even though we're dealing with y. This is the formula that you saw before. Let's see. And that's the formula we're going to use to do our calculations with. So let's just plug and chug in. So we've got, let's see, x is 0 minus 0.3333 squared times its probability, which is 0.6667, and then plus, let's see, 1, right, that's the probability, or I mean that's the value of y, minus the mean again, 0.333 squared times 0.333, and all of that together comes out to 0.0741. So we got this one. Check. Are x and y independent? Well, we can figure this out. The probability of x is equal to 0. Let's see. Well, we've already figured that out. That's right up here, right? So we've got 0.644545. What's the probability that y is 0? Well, let's see. We've got to go through, and essentially that's y is equal to 0. That's one probability. Here's another one. And we've got another probability of y is equal to 0. See, we're just figuring out the marginal probability that y is equal to 0. And we've got a lot of them. So we've got to add them all together. If you add all of those numbers together, you should get something like 0.2240389. So the way we find out whether these are actually independent is we're going to just take this f of x at 0 and the probability of y at 0, multiply them both together. So we've got both of those numbers, and we can multiply them together. And if you multiply them together, you're going to find, let's see now, 0.1444, and that is, let's see, well, let's find out what is the probability of x and y is 0. That's f x y 0 0. That number is right up here. Calculated it before, and it's 0.116 blah blah blah, right? And we're finding out that the probability of x is 0 and y is 0, which is 0.116 blah blah blah, is not the same as these two marginal distributions, f of x at 0 and f of y at 0. They're just not the same. So are they independent? Are x and y independent? No, they're not. Alrighty, so now we've got to determine the value of c, the constant that makes this function a joint probability mass function over the points from x is equal to 1, 2, or 3, and y is equal to 1, 2, or 3. So, well, the big clue here is what's going to make this a probability mass function? Well, that's pretty straightforward. All we have to do is make it so that if we sum up all of the probabilities for each x and y over the entire range, well, it's got to be equal to 1. So if we want to, we can write this out a little bit more specifically. We can say, well, looking at this function exactly, if we take c times the summation over all the x's and over all the y's of x plus y, it's got to be equal to 1. So, well, let's just kind of do that. So we'll say that c times, well, let's see, we'll get a sum. Let's see, the first one is going to be x plus y. Let's take that x is 1 and y is 1. So x plus y is going to be 1 plus 1, which is 2. So now next let's go to 1 and 2. Well, that will be, plugging things in here. It's 1 plus 2 is 3. And if we just kind of keep going along in that sequence, it's going to be plus 3, plus 4, plus 3, plus 4, plus 5, plus 4, plus 5, plus 6, and thank goodness they didn't make it any bigger. And all of that, as we see here, has got to be equal to 1. So if we sum everything all up, we find that c times 36 is equal to 1. In other words, c is equal to 1 over 36. Aha! This is a good thing. Okay, so now we can begin solving the rest of this problem. But before we even do that, let's kind of play a little trick. Let's see here. If we wanted to, we can make ourselves a handy-dandy table. And the handy-dandy table will go like this. We know we've got x's, right? So there's our x, and we know we've got y's, And let's see, the y can range from 1, 2, and 3. So let's draw a little line here. We'll make it all nice and neat. And x can go from 1, 2, and 3. Okay. Now, all we have to do is plug in. We know that the formula is essentially just right up here, circling it. So f of each of those x's and y's is 1 over 36 times x plus y. So what is this, the first in the table here, the first thing? Well, it's got to be 1 over 36 times 1, right, because x is 1, plus 1. Oh, that makes 2 over 36. Huh, well, that's pretty easy. How about this one? What is that? That's going to be 1 over 36 times 1 plus 2, right? So that makes it 3 over 36. And what's this one? 4 over 36. I mean, this is all pretty easy. If we calculate here, we're just, okay, go over here. Here's the x. X is equal to 2, so it's going to be 1 over 36 times 2 plus, well, 1. Oh, okay, so it's 3 over 36 here. And we keep on computing, and we put everything in its place quite nicely. 5 over 36, and here we've got 4 over 36, 5 over 36, 6 over 36. Oh, hey, this is so easy. I love it. You know, in fact, this is so easy that why don't we do something? We're going to, actually, while we're at it, I mean, we're already here, why don't we put down the marginal distributions? So how do we get the marginal distributions? Well, let's see. Y is 1. It's going to be 4 plus 3 plus 2. And that's just going to be 9 over 36. And adding likewise along this axis is going to give us 12 over 36. Whoops, 12, count 12, 36. And this one is 15 over 36. And over here, we're going to have, counting up everything over here, is 4 plus 3 plus 2 is 9 over 36 on this margin, and 12 over 36, and 15 over 36. Oh, these are so nicely symmetrical. I love it. Okay, now that we've got this table, everything else in the whole darn problem is really easy. Because look, the first one, let's look at this. It's saying the probability of x is equal to 1 and y is less than 4. Well, that means all of these, it's like y is 1, 2, or 3, and it's only the first row. So that's pretty straightforward. Let's write it out. A is 1 over 36 times, well, let's see, we've got 2, 3, and 4. 2 plus 3 plus 4. And if you calculate that all out, it's just 1/4. Well, that's pretty easy. What about part B? So it says x is equal to 1. Let's see, x is equal to 1. Shouldn't that be the marginal distribution here? Huh, yeah, it should be. So it turns out to be 9 over 36, which is 1/4. It's the same as part A. So now for part C, they want us to have, let's see, the probability that x is equal to 2 is just going to be 12. It's marginal probability, 12 over 36. If it's the probability of y is equal to 2, it's going to be just kind of looking on this column, and it would likewise be 12 over 36. And so it's 1/3 essentially. Now, let's see, the next one is the probability that x is less than 2 and y is less than 2. Well, look at that. Less than 2, less than 2. We've only got one option. That's 2/36. It's, the probability of x is equal to 1 and y is equal to 1. And that gives us 2/36, or 1/18. Oh, that's easy. Okay, now let's look at part E. So we got to do a few little calculations, but they're not that bad because we can see everything here on the table. So for part D, we take e to the x. Simple, just take that first 1. What's the probability that that 1 will occur? Well, 9/36. Easy. And then 2 probability times the probability that the 2 will occur, which is 12/36. And then plus 3 times the probability that the 3 will occur, which is 15/36. And that all ends up being 2.167. Oh, okay. So that if we calculate the variance, then it's just, we kind of use our same old formula again. We're going to have 1 minus 13/6 squared, right, because we already found what that mean is right there. And multiply that times 9/36. And then plus 2 minus 13/6 again, squared, times 12/36, plus 3 minus 13/6 squared, times 15/36, and all of that equates to 0.639. And then you'll just have to trust me, or better yet, you can work it out for yourself. You can find that the expected value of y is similarly 2.167 because it's a symmetrical matrix there, and v of y is going to be 0.639. So now it's asking for the marginal probability distribution of x right there. Well, guess what? We've actually already calculated it right there, right? So it's right along these margins here. There, I've switched everything over to the next page. So let's move on to G now. Conditional probability distribution of y given that x is equal to 1. So that is basically, you can think of it as f of y given that x is a certain number, y, is equal to that distribution given that x is 1 of y, all within the world of f of x is 1. Well, you kind of know what this number is, right? Because it's just the marginal probability right here, 9/36. So that's 1/4. So we can calculate, well, let's make a little table here. We'll say y and f of y x, right? So we calculate it out for 1, 2, and 3. And let's see. So we know that underneath, we're just going to use this formula up above here. So underneath is going to be 1/4 all the time, because that's actually 9/36. That's the marginal distribution of for x is equal to 1. So if we plug in x is 1 and y is 1 right up in here, then we get, well, 2/36. So that whole thing becomes 2/9. And similarly here, we've got 1/4 again on the bottom. For 2 and 1, we'll have 3/36. So that will become 1/3. And then 4/36 over 1/4 will give us 4/9. And so there we go. We've got our distribution here of y given that x is equal to 1. So we're only within that world. So they absolutely want to beat this to death for you. So now they want you to do for y is equal to 2, right? So, okay. So let's see. Y is equal to 2. So we're going to do the same, we're going to play that same old funky music, as they say. And we've got x, and then, let's see. Don't look at that. Okay, so we got f x y, x is 2, and that's an x right there. And then we've got f y of 2. And, well, what's the marginal distribution for y is equal to 2? It's 12/36. So that's actually 1/3. So let's just do the same table here. So now we're doing, let's see, this time we're going to, so we're fixing y at 2. And so we're going to say x can be 1, 2, or 3. So we go like this, we go like this, and, oops, we make a little zigzaggy line, f x, given that y is, some function of x. So basically, we're using this equation right up here. So the world we're living in is that marginal probability where y is equal to 2, and that is going to be 1/3 on the bottom, right? Because we already found it over here. That's this 12/36. And then on the top, it's just going to be, well, let's see, x is 1, y is 2. So that means 3/36, right? 1 plus 2 is 3 over that c value, or times the c value, which is 1/36. All of this becomes 1/4. And then similarly over 1/3 right here is 4/36. And that becomes 1/3. And then 1/3 of 5/36, right? And that becomes 5/12. So we've got it. There we go. And now we're on to the expected value of y, given that x is equal to 1. So we're going to have, let's see, this is I, e of y, given that x is equal to 1. X is equal to 1. And that's just going to be, let's see, 1 times 2/9, right? So it's plus 2 times, well, you can kind of guess it's going to be 1/3 plus 3 times 4/9. And all of that becomes 20/9. Now, are x and y independent? So that's part J. Well, remember, what we're going to do is we're going to take those two marginal probabilities, which are 9/36, right? That's the x is 1, and y is 1. The marginal probability is again 9/36. And if we multiply that all out, we'll find that that is 0.625. And guess what? That value is not the same as 236, which is right over here. And we've got 236 is actually 0.05 if you work it out. And so we have just shown that they are not independent. Check. Congratulations, you finished.